All right, let's do a few more derivatives, but before we start, let's remind ourselves about the chain rule, right? So, and I'll illustrate with this first example, number 32. So the idea there was that, that's if you have a composition of functions. So like in this example, sine of x squared, the first thing you're doing is you put a number and you square it. That's kind of the first layer. And then you take the sine of it, right? So the way I always picture this in my head is like, here's x, it goes into some function machine. Let's just say g of x. And it spits out some other variable u. I always think of like some sort of conveyor belt here that the numbers are chugging along. That was not a very good conveyor belt, but you know what I'm saying. And then it goes into another function. And I kind of don't even want to write g of x. I just want to like g of almost like a blank space. And then f of, you could say f of u, but it's f of whatever you're plugging in, and then out comes y. So for example, in 32, you have x going into the into the squaring function. You're squaring whatever you put in. And it comes out, let's call that u. So that's x squared, which we're going to call u. And then that's going to go into the sine function. Sine function. And then spits out y, which is sine of u. Right. So that's the that's what we mean by a composition of function. It's like a multi-stage function, right? And if you remember, if you have this y equals f of u equals g of x, then the derivative of y with respect to x, the chain rule says that dy dx, it's dy du times du dx. The derivative of y with respect to x is the derivative of y with respect to u times the derivative of u with respect to x. And this is another reason why the Leibniz notation is nice, because if you think of these kind of look like fractions, and it's like the du's cancel and you get dy dx. So it actually makes some sense, hopefully. And then in this example, well, dy du is f prime of u, and du dx is g prime of x. So you could say that's f prime of u times g prime of x, right? And here y is f of u, and u is g of x. Okay, so what's f prime of u? Well, in this example, so for example, the derivative of, I guess we're looking at 32 explicitly now, the derivative of sine of x squared. So the f in this case is the sine. So that's like, and if we're thinking of, you're supposed to think here of u as equal to x squared. So u equals x squared. So this is really the derivative of, it's f prime of u. So f of u is sine u. So the derivative is cosine u, right? So you get cosine of u times times g prime of x. Here, g of x is x squared in this example. And so g prime is 2x. So times 2x. Okay, so the answer, you could say the answer is cosine of u times 2x, but we don't want to answer in terms of u, so you're going to plug the x squared back in, right? This x squared is going to go back in for u right here. So, and I'll put the 2x in front. So this is really 2x times cosine of x squared. Okay, so that's the answer. But in practice, we don't want to write out the whole dy, du, du, dx, identify u, identify f and g, do all that stuff. We don't really want to do all that. So what we'll do instead is, I like to think about differentiating layer by layer, because that's kind of what we did, right? We differentiated the sine layer, and then we multiplied that by the derivative of the squaring layer of the function, right? There's kind of two layers of the function. It doesn't matter, since we're multiplying, it doesn't matter what order we do it in, but So derivative of the outside layer was a sine, gave us that. And then the derivative of the sort of inside layer, which was the x squared, gave us that. So in fact, when I write these for myself, I usually do something like the following, especially if it's complicated. I'll just put or here. So I usually think, okay, well, I'm going to differentiate this outer layer first, right? Let's differentiate this layer. This layer right here, the sine. So that becomes, like we know, cosine. So that's cosine of the same thing, of x squared, times the derivative of the inside function. It's one reason this sort of d over dx notation is nice, because you're actually creating, I mean, you're actually giving, it's like an instruction. It's like take the derivative with respect to x. So you can actually just push, it's almost like we pushed it through the sine, got a cosine, and now we have to apply it to the x squared, right? So that's cosine of x squared times 2x, which, like we said, is 2x cosine x squared, is the way we'll tend to write that. Okay, so that's number 32. So try to remember, to see if you remember the chain rule again. There's some other 33 and 34 and 35 are really, all of these are more chain rule examples. So let's just power through a bunch of them real fast, doing it this process that I talked about, where it's like, let's just differentiate layer by layer. So 33 is x cubed minus 2 raised to the 5th power. And really what I want to do is differentiate that. So let me put the d over dx in front of it. And notice what you see, it's almost like if you make the x cubed minus 2 blurry and don't worry about it, it's just something to the 5th power, right? So how do we differentiate something to the 5th power? Well, it's 5 blah to the 4th, right? So it's 5. I wish that looked more like a 5. 5 times x cubed minus 2 to the 4th power times the derivative of the thing I sort of blurred out, the inside. The inside is this x cubed minus 2, right? So it's like we reveal this now, and then that's really what we're going to differentiate. And so that's just times 3x squared, right? So that's 5 times x cubed minus 2 to the 4th power times 3x squared. Minus 2 goes away when you differentiate. So this is 15. If I multiply the 3 by the 5, that's 15x squared times x cubed minus 2 quantity to the 4th. So that's an example. Okay. So it's the same process. 34, again, you might want to be pausing and trying these yourself. 34, square root of x squared plus 1. So let's differentiate the square root of x squared plus 1. Well, before we do that, we probably want to convert that to a 1/2 power, right? And so again, the inside thing is the x squared plus 1. So we're doing something to the 1/2 power first. I mean, at the outside layer, we're actually not doing it first. We're doing the last kind of. If you're plugging in x in this function, you're squaring it first, then you're adding 1, and then you're taking the square root. So the outer layer is the 1/2, the square root. So that's 1/2. We're applying the power rule, x squared plus 1 to the minus 1/2 times the derivative of x squared plus 1. So that's 1/2. X squared plus 1 to the minus 1/2 power, you could write as 1 over the square root of x squared plus 1. And then the derivative of x squared plus 1 is just 2x. Now let's see, these 2's cancel. And really you just get, looks kind of nice actually, it's x over square root x squared plus 1. Okay, so that's that derivative. Let's keep going. Am I going to really do all these? Might as well do most of them. 35. You know, maybe I'll skip 35. You kind of get the idea, right? You're just going to write that as x cubed plus 1 to the minus 2 power. Just write the whole x cubed plus 1, write it to the minus 2 power instead. Might write that out yourself if you want to see if you get the right derivative. I'll just tell you the answer. I should be able to do this kind of thing in my head. No, I can't. Can I do that in my head? I'm not that good. I guess I'm just going to do all these. See if you can do it yourself, though. I don't know. For some reason, I really stupidly thought I could do that in my head. Probably could. It's probably minus 2 x cubed plus 1 to the minus 3 times 3x squared is really just all it is, right? So maybe I'll just write it of 1 over x cubed plus, I keep forgetting what the numbers are. X cubed plus 1 quantity squared. So that's negative 2 x cubed plus 1 to the negative 3 times 3x squared, which is negative 6x squared over x cubed plus 1 cubed. Okay, that was a faster version of that. You know, don't get that fast until you're sure. 36. What's 36? Sine of e to the 5t. Oh, this is a nice one. So notice differentiating with respect to t now. Sine e to the 5t. Now, really, you can think about this as sort of 3 layers. Sine, the sine layer, the exponential layer, and then the multiply by 5 layer, going from outside in. So that's cosine of e to the 5t times the derivative of e to the 5t, which, again, I could write this layer by layer if I wanted to be really careful. So that's the first layer differentiated. The next layer differentiated is that we know that the derivative of e to the something is just e to the something. But we still have to differentiate the something. We still have to differentiate the 5t. Right? And then that'll just be a 5. So that's cosine of e to the 5t times e to the 5t times 5, which probably I would write as 5e to the 5t times cosine e to the 5t. Okay, good. 37, cube root of cosine u. Not bad. Cube root d du, that's cosine u to the 1/3 power. So that's 1/3 cosine u. We differentiate the 1/3 power is the thing outside, right? So the 1/3 to the minus 2/3 times the derivative of cosine. Again, if I want to be careful, make sure I'm doing the right thing, I can always write this step first. And then that's 1/3 cosine u to the minus 2/3 times the derivative of cosine, which is minus sine. And so you could rewrite this all as, if you want, minus sine u on top 3 times the negative the 2/3 power, the negative put it on the bottom of the fraction. The 2/3, it's the cube root of cosine u squared, which we write cosine squared u. You don't have to write it this way, but you know, you could write it that way if you want it to be a little more concrete. Okay, almost done. 38. I like this one in particular, ln of e to the x and e to the ln x. Let's differentiate ln of e to the x and see what happens. Oh, geez. D over dx of ln of e to the x. Well, the outer layer is a natural log. The derivative of natural log is 1 over, right? So that's 1 over the thing inside times the derivative of the inside. But that's just e to the x again. So we get 1 over e to the x times e to the x, which is really just 1. That's kind of surprising. what function, whose derivative is 1? X. The derivative of x is 1, right? But d over dx of x is 1. And in fact, it's true that ln of e to the x equals x, because the natural log and the exponential function cancel each other out. They're so-called inverse functions. So that makes sense, actually. In fact, we could have just converted that to x and then differentiated and got 1. But if you didn't notice that ln of e to the x equaled x, and you differentiated, you get 1 anyways. So that's kind of nice. Similarly, e to the ln of x is x. Doesn't matter what order you do the two functions. If they cancel out, they cancel out kind of in either order. It's like multiplying by 2 and multiplying by 1/2. Those cancel each other out. It doesn't really matter what order you do that in. So if we differentiate that, just to check that we get 1 again, we should get 1 again. Well, the outer layer is the exponential, so that doesn't change, times the inner layer, which is the natural log. So the derivative of that is 1 over x. So we get e to the ln x times 1 over x. Does that equal to 1? Well, yeah, because this equals x again. So this does equal to 1. Here, it's not as obvious that it gives you 1, but x times 1 over x is 1. Okay, and I know this is getting long, but let's just power through the very last one. We'll have done so many derivatives. X, can I cut and paste this? I can't remember these. Maybe I can copy and paste this. Let me try. So, yeah, there it is. Okay. Oops. All right. So if we do the derivative of this, well, there's a lot going on here, right? But the first thing I see is that there's a product. It's x squared times the sine of something. Sine of something horrible, but it's times the sine of something, right? So but the outside thing, it's almost like the last thing we do would be multiply these together, because we'd compute x squared, we compute all this nonsense, we take the square root, we take the sine, and then last thing we do is multiply them together. And so that's first thing that's going to happen is a product rule. So it's the first times the derivative of the second. I'm going to write that as e to the 3x to the 5th minus 7 all to the 1/2 power. Plus the derivative of the first, which is just 2x times the second. So sine of square root e to the 3x to the 5th minus 7. Okay, close enough. All right, so now we're down to having to deal with this. And this is a chain rule problem again. This is going to equal, so we differentiate the outer layer, we get cosine e to the 3x to the 5th minus 7 to the 1/2. And then the next layer is the 1/2. In fact, I almost should have put more parentheses here just to be careful. Like there's really like another parentheses there. Sine of all of that. So it's cosine of all of that times the derivative of that e to the 3x to the 5th minus 7 to the 1/2 power. Okay, well, the outermost layer now is the square root, the 1/2 power. So that is going to be, so this is just, I should have been doing this all in orange actually, because I'm just doing this part. So can I make this all orange maybe? Yes, look at that. Okay. Let's stick with the orange. So that's, so we've got this cosine of the square root of e to the 3x to the 5th minus 7 times the derivative. So times the derivative of the square root, right? So we get 1/2 e to the 3x to the 5th minus 7 to the minus 1/2. That's that layer. And then times the derivative of the inside. So the derivative of the e to the 3x to the 5th minus 7. Whew. Okay. So that is, I'm just going to start being a little bit lazy. The same thing times the same thing. Now we're differentiating the exponential function because that's the outermost thing, right? We're doing e to the 3x to the 5th minus 7. So that's just going to be e to the 3x to the 5th minus 7 times the derivative of 3x to the 5th minus 7. And that one's easy. It's just 15x to the 4th, right? So let me just write that. So we get same things from before. This is the same as before times 15x to the 4th minus 0. So all that stuff, all this stuff here, this term times this term times this term times this term is what needs to go right here. So our final answer, if we just copy all, that's going to be ugly. So I think the final answer is x squared times all this orange stuff. So cosine of the square root of e to the 3x to the 5th minus 7 times 1/2 e to the 3x to the 5th minus 7 to the minus 1/2 times e to the 3x to the 5th minus 7. If you're still watching this video, more power to you. Times 15x to the 4th, all of that, plus this stuff right here. Plus 2x times sine of the square root of e to the 3x to the 5th minus 7. Okay, and I mean, you could clean some stuff up here if you wanted to, like there's a 1/2 times a 15. This is a minus 1/2 power, so you could put that on the bottom as a square root. Actually, there's some simplification here because these you can multiply together. Is that right? Did I do anything wrong here? I'm worried I did something goofy. Let's hope not. So now, and then you could also combine the x to the 4th here and the x squared here. Well, now I sort of want to combine stuff. So first I claim, I'm just gonna keep going with this for a little bit. First I claim this is like the +1 power, and then you're gonna add the powers. So this times this is actually gonna give you a +1/2 power. Oh, I know why. Okay, I see why. I'm being kind of silly. I see why this is going to happen. Yeah. Okay. So this is actually e to the 3x to the 5th minus 7. It's really to the 1/2 power, so it's the square root of all that. So just in the name of cleaning this up as much as I can, we're going to get 15/2 x squared times x to the 4th, x to the 6th, times the square root e 3x to the 5th minus 7 times cosine of the square root of e to the 3x to the 5th minus 7. I think that takes all those terms into account. Plus 2x times sine of the square root of e to the 3x to the 5th minus 7. Okay, so that's the final answer to that question. There's no reason to ever differentiate anything this hard. I'm never going to ask you to differentiate anything this hard. on a test or anything. It's just to show that you can, just to prove that you can do it. I will say the one thing that I probably could have made my life a little easier, and why this ended up happening right here, is really, let me just write this as an aside, that the square root of e to the 3x to the 5th minus 7 is actually e to the 3x to the 5th minus 7 to the 1/2 power, like we mentioned. But there's successive exponents here. We do this exponent, then this exponent, and actually, in that case, you just multiply the exponents. So you could actually write this as e to the 1/2 times 3x to the 5th minus 7. So we could have actually combined those two layers into one layer, which would have made life a little easier. But whatever. Okay. Okay. If you made it this far, again, you win. I feel like I should give you a secret word that you can put on like a test to get extra points or something. What's the secret word? The secret word is Searles. If you write Searles, the name of the building, the math building, if you write Searles in all caps on your test, I'll give you like an extra bonus point on your midterm. Okay. I'll stop there.